Hello everyone, welcome to my YouTube channel. Thank you so much for your amazing response, feedback, and awesome comments. You all know that I'm doing podcasts on quantum computing. I have discussed so many important parameters related to quantum computing with so many experts across the globe. In this context, today we are going to discuss one of the most important part of quantum computing, that is all about programming. Programming is the heart of any technology. People fear with programming, but some people really love programming. So we have one of the expert, very young and dynamic expert, who is going to discuss all the important points regarding the programming languages he has expertise and the projects he has developed in the area of quantum computing, which is very, very important for us to know. As a student, as a developer, as a professional, as a researcher, if you have very good grip on programming languages, definitely it will help you a lot in your near future. Not wasting your valuable time, I'm going to discuss about the today's guest in very short manner. So we have Kaue, who is a developer who has done lots of work in quantum computing. He is expert in Java. He is expert in Python and other languages. He has done so many good projects in the area of quantum computing. We are going to discuss what is his personal journey in this area and how he has masterized these many programming languages. I request all of you to watch this podcast from beginning to ending. Do provide your valuable comments and do let us know what did you like in this episode. Thank you so much, Kavi, for joining this podcast. Can you please introduce yourself?
Hey, thanks Rajesh for the opportunity. I'm Kaue from Brazil. So I work mainly with some backend and mobile projects, especially Java, Kotlin, Python, some Go. I have worked a bit with C and Rust, especially for OS and cluster computation. And recently I've been studying quantum computing, especially in Python, in Qiskit and Quantum. So, yeah.
Okay. That's good to know, Kavi. As someone fluent in both Kotlin and Qiskit, how do you see the line between classical and quantum programming starting to blur?
So as of recently, we've been seeing every day way more research being made on hybrid computation, be it on hybrid, actually hybrid algorithms, or to bridging together backend technologies and quantum technologies, such as IBM Quantum Platform or AWS Bracket, which lets you to run quantum algorithms on their real hardware and then integrate via cloud. So it's become way more easier by each day to actually program some backend and then call quantum code from it to integrate to your classical app or website, be it a standard website or mobile app.
Okay. So he to know what was that one aha moment when you realized quantum computing wasn't just theory, but something you can actually code.
So it was probably when I first heard of VQE and such hybrid algorithms. So I've had studied quantum computing before that, most of the theory, and I do like theory researching. I've always been interested in quantum mechanics, more from a mathematical approach. But then when I first seen a VQE running and its possible applications, was when I realized that we can actually use, and it has been used recently and will be in the near future to develop new algorithms. And already has some even market and enterprise applications.
Okay. If you could rewrite one part of the current tech stack, backend or quantum, what would you completely reinvent and why?
So I'll probably neither rewrite nor the backend itself nor the quantum itself, because most backend technologies are well established in the market. For instance, Java and Spring are over 20 or recently Java has turned 30 years, right? Or 35. So it is a well established environment with many developers, and you wouldn't make a it wouldn't really make sense to rewrite everything. And on the other hand, the quantum technologies are too new, so they are already being reinvented by each day. And sometimes we have some hardware improvements, and then we rewrite the quantum SDKs to reflect the hardware. Sometimes we improve the logic behind that or the physics, and then we adjust again the SDKs. So if you write the quantum specific SDKs, it will be just another rewriting or a new framework between many others. So I will probably rewrite the middleware, not the backend nor the SDK, but the bridge between them. So cloud environments or APIs and gateways to actually bridge the backend to call quantum code, especially if we can make it platform agnostic. So it doesn't matter for the backend if you're running Qiskit, Penguin, D-Wave, Bracket. You just need to call the actual quantum code.
Okay. So your VQE project on portfolio optimization sounds fascinating, Kaue. How close are we to the world where quantum finance replaces Wall Street algorithms?
Oh, it's actually extremely far. And I don't really believe we should aim to replace the standard algorithms. Because, first of all, the quantum hardware needed to run it is not ready for large scale applications that we would need for. So we don't have that many qubits ready with error correction or mitigation to run large modules or big VQE, KOA, or even other algorithms. And the classical algorithms are proven to work. Maybe not the best versions. It may be the quantum versions are slightly better or even way better, but in general, time has proven that the classical algorithms already work well enough. And at the same time, for our current research and state of art shows that we have some quantum algorithms that may demonstrate some advantage compared to their classical counterparts, but we don't have any mathematical proof that actually demonstrates that there will always be the case that a quantum is better than the classical. In general, I do believe we should aim to integrate them. So we have the classical basis, which has been worked for some time. And besides that, we integrate quantum with quantum technologies, be it quantum algorithms or quantum hardware, to leverage advantage where it's possible.
Oh, yeah. For students who think quantum is too hard, what's the mindset or habit that helped you cross that learning wall? Because this people, especially students, they feel quantum computing is very tough to program. So, how to start programming in quantum computing? What was your own experience? Can you please share that?
So I think the major mindset change you must have, and which has helped me in the past, is that you don't really need to master quantum or have any PhD in physics to actually start coding. So with the basics of Python programming, which is actually the one of the easiest language to start learning how to code, and some fundamental linear algebra like vectors and matrix operation, you can already start to comprehend quantum phenomena, mainly superposition and entanglement. And with that, you can start to read and even code in platforms such as Penelane and Qiskit. So we don't, I think that's the major mindset. You don't really need to have years of study before starting. It's not like you will have a job right after you begin, but and you won't either be able to fully comprehend what's going on, but you can already start. And by starting, you can create a habit of constantly studying. And with that, when the time passes, you eventually become more comfortable with technologies and start to migrate to more complex topics.
Superb. That's a very good advice, Kaue. If Google, IBM, and OpenAI gave you a blank check to build any hybrid classical app, what would you build first?
So I'd like to run some benchmarks maybe. So in VQE, for instance, we have the ansatz, which are some circuits we can use to optimize our code. And it would be nice to have this blank check to test everything, especially in real hardware with error correction and mitigation techniques, with and without them, so we can compare the results. And especially right now, we run mostly on simulators, on my project at least. And the simulators are too different from the actual quantum computers, even with when we simulate the quantum noise. So it would be really nice to test our toy projects or even real projects, and in any ways we please without having to mind the final cost of the cloud.
Okay. In Android and backend projects, performance tuning is key, as you know. Do you see parallels in how we optimize classical versus quantum algorithms?
Sure, there are some similarities, especially when you consider some time constraint computation in classical computing, such as embedded projects or performance critical, where you have limited amount of resource, be it RAM or storage, and you have to fine tune your application. You may not be able to use too generic technologies or stacks, and you might have to recur to more of when and for lower level language such as C or even assembly in some cases to optimize your project or optimize your code to the actual project. And most times in quantum, we actually we need to think in a similar way. So we don't really have that many qubits on real hardware, and it's really costly for a classical computer to simulate many qubits. My notebook, for instance, I can run around 12 qubits maybe, and after that it starts to consume too much RAM. So most times we do need to design our algorithms specifically to that problem, and considering that we won't really be able to run with too many resources, yes, RAM, qubits, and always considering the noise. It's another layer of complexity that we don't really have in classical computation.
Okay. What's the biggest misconception people have about quantum computing that makes you want to yell, no, that's not how it works, especially as a programmer? What you want to say here?
I'll say something similar to the current AI hype. And as an AI PhD, you probably experience something similar in your field. So everyone's saying that classical computation is going to die or be replaced either by AI or by quantum, but that's not really the case. As we discussed before, I don't see that quantum should and will be a replacement for classical computation. There are some problems that quantum can, and quantum have too many advantages compared to classical computation, such as Shor's algorithm, for instance, for cryptography or breaking cryptography, and some machine learning projects that quantum algorithms can experience more performance. But again, that's not really the case for all of the projects, possible all situations. And we also have the opposite. Like we have some situations where a classical computer is more suitable than a quantum. And maybe most of the situations are like this. We cannot expect to have a quantum only website, a quantum backend, or a quantum operating system. So, as always, my opinion is that we should leverage advantage of which type of computation is more suitable for that specific task. So, as always, integrating quantum and classical and not trying to replace classical for quantum.
Yes. So when your quantum code finally runs correctly after hours of debugging, what's that feeling like compared to shipping a Spring Boot API?
It's overall way more gratifying to actually run correct quantum code because, sure, there are some complications in backend development, but you can always write your tests and fine tune your framework code like JUnit to help you to ensure your backend code is running as you intend them to be. And you may have integration tests to make sure the front end always responds as you expect. And as it's not as easy as it sounds, there are ways, well established ways, to make sure your code works as intended. But when we're talking about quantum, the probabilities and overall unpredictability is the very foundation of quantum mechanics and by extension quantum computation. So sometimes you do have your tests or you have mathematical proof that your algorithm will always have the same expected outcome, but at the same time you could run your code on real hardware and then by the coherence or other errors, you actually get the wrong result. It might be misleading and very hard to debug. So in the end, uh, running correct quantum code is more. It can be harder, and then it's a better feeling when you actually manage to do it.
Yeah. Fast forward 5 years, will quantum developers be the new AI engineers? And how can today's students prepare before this wave hits?
So first of all, how can today's students prepare? I guess it comes back to what we discussed before, such as start studying the basics and then eventually study more complex topics and always try to run maybe some challenges like Pendelane has some interesting tutorials and sometimes hackathons to apply the concepts so you can eventually get ready and more used to read about quantum computation and write your own quantum software. And will the developers be the new AI engineers? So if we consider the actual AI engineers like yourself, people who have degrees and study actual artificial intelligence and not just marketing or LLMs, they are we can see many similarities. Like most of correct me if I'm wrong, please, but as I've heard, most of AI math background has been already developed from the 50s and 60s, but only now we do have the hardware resources and actual actual programming language that can handle all this math, so we can make actual models and run our models, train them efficiently. And that's why in recent years we have seen way more AI applications and development. So in quantum is actually similar in sense. Since from the 80s it has been studied. From the 90s we had some theoretical algorithms such as with real applications such as Shor's algorithm or Grover's algorithm. But only now we have the quantum hardware to start running them and research on hybrid algorithms so we can run our code in near-term hardware and researches. So in sense, yeah, maybe not the all of the hype or actual applications will be the same level as AI, but there are some similarities. I just don't think it will be as available as a job market. Just in as in, we won't have that many quantum specific jobs opportunities for everyone in 5 years as we have now with AI engineering and related fields such as data science or data engineering, data lakes, and so on.
Yeah, super, Koi. I really appreciate your pointers towards the programming language and how to expertise in this area. You have provided very good information about how to be a very good programmer in this quantum computing area. That is very much helpful for so many students who want to grow in this area. Thank you so much, Kavi, for your valuable time. I wish you all the best for your future endeavors, and we want to see more and more useful projects from your side in terms of quantum computing. Thank you so much, Kavi.
Thanks so much, Rajesh, for the opportunity and for the talk, and have a nice day.
Yeah, thank you.